Okay, it is 10 o'clock or 3 o'clock or another time, depending on where you are. So let's get going.
Okay.
All right. Welcome back, everyone, to the second episode of the Ecological Psychology Seminar Series. We are very excited to be joined by Damian Kelty-Stephen of SUNY New Paltz. And Damian's there. And Damian is a key researcher within ecological psychology and surrounding fields as well. And he does a lot of work in a range of different areas, but multifractality, I think, is what a lot of us know him for. And I think I'm probably speaking for a lot of you when I say that he is a very positive presence on social media, and he's given a tremendous amount of help to a lot of people within academia and outside as well. And his work is really a pleasure to read at any level. So we're really excited to have Damian on.
Well, thank you very much. Thank you for those kind words. And thank you for having me on to talk. I'm really looking forward to sharing a few ideas here and opening up some questions and seeing what people think. So do we just get started? Or
Damian,
what?
I will welcome you to share your screen.
Okay, great. Here we go. So ecological psychology offers a few exciting challenges and a few exciting ways forward. And I'd like to focus today on the way we can sort of situate action and aim it towards the future. So as we meet ongoing constraints be they in the context or constraints in the body, I'd like to propose that we navigate and make use of those constraints by embodying a distinctively multi-scale organization that we can call a cascade, which is a rather colorful term, but it's also a firm body of formalism from mathematical and statistical physical fields. Cascades offer an exquisitely context-sensitive way to describe and perhaps to explain how we relate to our world at multiple scales, both near and far, spatially, and both in the present moment and onwards into the future. So to open things up, I'd like to recall what I hope is sort of a well-known cultural touch point. I've recently bin watching the Star Wars movies with my kids. This is my receiver isn't working. There we go. So we in the climax of the Star Wars movie episode 4, A New Hope, we find Luke Skywalker flying very close to the Death Star, hoping to drop a depth charge into a gap in the shields. And the advice he gets through the galaxy is to turn off the targeting computer. And so he has to use the Force instead. So his goal here is to sort of aim this target into the context. He's hoping that it flies somewhere into the future beyond where he is. And then he has to sort of aim his own behaviors away so that he can get to safety. And so his advice from Obi-Wan, I believe it was, so use the Force. So turn off the targeting computer. This is sort of this kind of encapsulates what I feel a sort of a nice, in sort of accessible terms, what ecological psychology asks us to do. So if we sort of undress this point from the pop culture example, a deep question for ecological psychology is, I think, that if we don't want inferential processes to be the foundation of perception, then what else do we have going for us? So what do we have to give us any chance of success, whether we're attempting to topple an empire or just sort of putt a ball into a hole on the golf course? So I want to sort of set some parameters, just because I know that ecological psychology is a very big field with a long history. And I know that the audience here is very diverse and coming to it from multiple levels and amounts of expertise. So I sort of want to set some of these parameters early on. We can come back to them later. I just want to sort of identify sort of my own feelings about some of these more basic issues here. I want an ecological psychology that's going to explain actual behaviors, which include, I would say, computing and predicting that organisms actually do. I feel like ecological psychology sort of distinguishes itself as an enterprise with this fundamental premise. The premise is that we're refusing to say that inference has to be a necessary causal factor. So it's one thing to say, okay, we're going to see how we can explain behavior without going to this fundamental backstop here. There's another step past that, which has to do with what we choose to study. And so there can be a refusal also, or not, to try to explain inferential or predictive behavior. So the difference is that one point is about whether it's primitive, whether it's supporting all the other perceptual stuff that happens. The other is whether it happens ever, and we'd like to explain how it happens. So I share the premise. So I would like for our explanations to turn off the targeting computer, but I then want to understand how we get by without that, but then also sort of how we do the things like predicting and inferring that seem to involve sometimes symbolic, sometimes computing processes. Now, there's a lot of important conversation that has gone on, most notably from the very eloquent encapsulation of Bill Mace, in which he said, "Ask not what is in your head, ask what your head is in." And I find a lot of truth in that, because it's basically saying we should focus on more than just sort of the brain, more than just what feels internal. We should look at our context, and that's totally true. But what I want to sort of add to this more and sort of emphasize is that computation, when we talk about inferring or predicting and all that stuff, it's not all or even mostly in the head. A lot of computation goes on outside the head. Attempts to get ready for the future, whether we're toppling an evil empire or we're just sort of reaching for a cup of coffee, those attempts to get ready for the future are important. And so I think that it's not sort of a distraction or a sideshow to understand how we gear ourselves up towards the future. And so I fear that if ecological psychology isn't careful, sometimes we can take our refusal to consider an inference, we can sort of accidentally potentially make that into a position that we'll never talk about it. And sometimes there is this ongoing question about, do we talk about inference? Do we talk about prediction? Do we talk about future tending behaviors? And if so, how? So I want to be able to say I would like to be able to talk about this sort of future tending aspect of behavior in a way that doesn't require inference, but that will someday explain how inference does happen. Okay, so the bigger picture for me about ecological psychology, I see it sort of holds a lot of promise. So the promise involves this way of treating perception and action as a coordination between constraints, as I noted earlier, and flows. And the flows are a very interesting, complex issue, which I'm just learning how, all the fluid dynamics that's out there, but there's a lot that I've seen so far that seems very promising for what it can offer to ecological psychology. Now, I want to sort of preface here, a lot of the thoughts and the reasoning that I'm about to go through, I owe to Howard Petit, Michael Turvey, and James Dixon. But so we have this balance in perception and action, and also other kinds of systems, but we have this balance between order and randomness, constraint and flow. So where your mind follows constraints you can't change, very often they're inherited, they're in the context, they're there, we're about to, we're about to meet them and haven't seen all of them by a long shot. But then the randomness, the fluid part is sort of where ecological psychology, I think, has a margin to sort of to explore this active role that we have in shaping our own experiences. And so in terms of physical principles and mathematical modeling and cascades, we have this sort of these possibilities of seeing how these two sides can interact. So do we get order from chaos, order from instability? And also on the other side, do we get randomness that's bounded by a more rigid context? So this balance, I would say, is tricky to pull off. And I think that one way to explain how it could happen is to look into these multi-scaled organizations. So trying to figure out how those balance together has led me to this idea of Cascade Dynamics. A lot of perception, non-ecological, has made very much of two major insights from Alan Turing. Alan Turing is one of my favorite scholars. I can't stop talking about him, it seems. But so I like very much how he had lots of independent insights that could be sort of put together in very, very creative and productive ways. And that you come out with these very interesting approaches to life and mind. So when I look through the history, I know there are many other things that he came up with. So this is not an exhaustive list, but one of the first insights that I find is his sort of resurrection of Bayesian inference. So he tapped into this understanding that if we have expectations of what the real stuff is out there, we can use it to sort of decode the incoming signals, even if they're encrypted, as they were in his particular circumstance. So we take our expectations of reality and we use them to sort of set up a landscape of prior probabilities. And we use those to sort of understand regularities that we might see in the stimuli-like signals that we don't understand yet. This taps into a longer historical background where Helmholtz had been asking in perceptual science, he'd been asking us to accept the idea that we did some sort of background unconscious inference that was based on sort of what we knew to expect, what we had grown to experience and expect in the world. Another of Turing's insights was the idea that computers can act like minds. He wasn't necessarily saying that the mind was a computer. He was very coy about this, I find. But he was very interested in seeing what sort of logical operations you could write and plan that could give you structures that look like mental states. So could you encode enough about reality and about the perceived signals? Could you give that to a machine and ask it to do logic that would produce impressions, like perceptual impressions? And so the example here was that came out was one of the earlier ones was the perceptron. This was not one of Turing's, but this device embodied sort of an integration of these two insights. So if you sort of know where to place the sensors, you can answer a certain set of questions about what's out there in the world. So and over the subsequent decades, beyond the perceptron, we learned how very much of Bayesian statistics could actually be run by computers. And that led to a lot of smart technologies. And it gave cognitive science a very interesting area of research where it could explore how these sort of predictive expectancy, expectation carrying machines could act context sensitively and prospectively. And that's been a very fascinating, profitable enterprise. I think that ecological psychology, and I'm not alone here, this is, again, I feel like it was Scott Kelso and Michael Turvey here, but I think in order to situate action in our context and to do a full-on ecological psychology, it helps to look at one of Turing's later insights, namely that subtle changes in context can lead to massive changes in behavioral outcome. And now this is something that an ecological grandfather, Nikolai Bernstein, would have gotten on board with entirely. This idea that subtle changes could lead to large behavioral response changes. So you didn't need to have an equal size cause produce the same size effect. What Turing was pointing out, though, he sort of saw all these computer logics unfold through these delicately organized machines. He realized, though, that the computer logic only operates within a set of expected stimuli. If you give the computer, like this this keyboard, a novel stimulus of spilled coffee, you're going to cause physics, sort of the melting and the sogification of your electronics, you're going to cause the physics to override the logic. Suddenly the logic, there might be a logic, but it's not the one that you planned because the physics has sort of undermined all that. So we have a capacity for new order, new structure driven by instability. So random fluctuations can produce new orderly patterns. We might not like the new orderly pattern, as in the case of our soggy computer, but that doesn't mean that it's not an orderly pattern. So for Turing's example, he was looking at morphogenesis and he was looking at genes and how they could help sort of coach structure to form in stem cells, but they weren't the whole show. They were background sort of supporting role actors, supporting randomly spreading chemical reactions. So his example was sort of a nearly uniform stem cell that's almost homogeneous, but has these very fine instabilities written into the what would be the individual little pixels here. And that if you let it flow, if you let it unfold, the reactions and diffusions of all those internal inconsistencies would eventually give you a dappled pattern, as you would find, say, in leopard spots or cowhide. So the idea here is that randomness can build coherent forms, not just any randomness, though. So, well, it seems to follow a certain progression, and it seems to have certain features. So we can look at fluid systems. So these are not living now. We can look at the example of Rayleigh-Bénard convection, where we start with a horizontal fluid layer. We heat it from below, and the heat source sort of generates a temperature gradient. So the heat is greater below than above. And so as we heat this fluid, we start off with conduction, which is just sort of the heat spreading randomly in different directions. It's a low-level solution to the problem of how to maintain equilibrium. As we increase heat, we steepen the temperature gradient. Then we get the emergence of these convection, these rolling convection cells that sort of spin in alternating rotational patterns. And so convection has these rolling cells, and suddenly the fluid has broken some of its earlier symmetry. So it's not all homogeneous. Now there's still sort of coarse forms here, but you can't sort of drop into any one part of the fluid and see the exact same dynamics as anywhere else. The fluid has sort of fallen into a distinct pattern where you can't overlap every segment the same way and get the same portrait. So this ends up being a slightly more efficient way to deal with the heat and to kick that out. And so this is sort of the way the fluid systems the fluid system has reorganized to deal with the problem of how to sort of kick out the excess heat. And so you get a shallower temperature gradient as a consequence of this new structure. If you keep heating it, then you get turbulence. So you can sort of completely unseat all the apparent symmetry here and get these very ornate, delicate, complex forms of swirls within swirls within swirls. So you get nested eddies of fluid flow. And so this leads to a very efficient transfer of heat, where heat can be passed along in different sort of size channels. Through each of those different size eddies, each eddy at different size can convey a proportional amount of energy. There's some very detailed modeling of this, but still it's sort of a challenging model system to sort of understand. We can understand the Rayleigh-Bénard model system as the ratcheting up of a control parameter from left to right here, where it's actually called the Rayleigh number, which is a function of several parameters that have to do with the context. So temperature gradient, pressure, length scale. So this would work differently if you were at higher altitudes with less atmospheric pressure. But this also implicates this control parameter. It implicates, by definition, a set of intrinsic fluid factors. So the viscosity, the thermal diffusivity, all of these are sort of entangled with one another as you pose this fluid system a more challenging contextual constraint. So this is not a living system, but so it's worth asking, where can we see perceptual systems organizing themselves in response to contextual pressures? Ecological psychology, I think, leans heavily into this idea that maybe we can learn from some of these fluid systems and how they flexibly respond to context. We can, for instance, find a self-organized or self-sustaining, once it's been started, system of touch, where we can look at the passive dynamic walkers. So these are they're just basically hips and legs. They have little eyes on the front with little ping pong ball halves, and that's cute. But basically, you just need to give it one push, one kick in the butt, and it'll keep walking. And it doesn't have vision, so it's about to walk into the wall there, but it will keep walking. It doesn't have sensors, motors, or controllers. It's just it's mechanics. It's mechanics with enough degrees of freedom to basically interact enough to give us that that sense of walking as falling and then catching yourself. And this used to need a sloped platform to work, but now it doesn't. What's happening here is that the initial push gets stored and recycled. So the mechanical degrees of freedom, which are sort of a complex feature that could, in one perspective, sort of require more control and more deliberate planning, those degrees of freedom, they actually end up solving their own problem because they end up sharing and interacting through all of these different mechanical events. So it's an honest question: how much perception might not need a nervous system at all? So we can really sort of push this envelope and ask, okay, so how much is actually mechanics? How much is actually physics? And obviously, I like my nervous system. I like you to have your nervous system. So I'm not saying we don't need that or don't use it. I just think that there's a deeper substrate here. And so this more detailed structure that we see in fluid systems that reorganize could offer a greater capacity to sense and respond across more scales. So we go from that sort of most homogeneous, least structured case of conduction. We get convection cells in the Baynard system as we keep heating it. And then we get turbulence, which is the least homogeneous. Seems like the most random, but it actually is, it has the most detailed structure. So we're going through a progression of no coherent response, slightly more coherent, but relatively simple. And then we get to our most context sensitive structure yet. If we could think about this responsivity of the turbulent regime, so we could look at the size of the eddies and the size of the swirls over progressively longer timescales, we would get something like this sort of power law relationship. So here we're just sort of it's relatively metaphorical right here, but we can think about the fluctuations of the fluid in this case as responsivity. It certainly will be once we're talking about an organism that's trying to perceive. Responsivity relates to the scale, so we can start to relate mathematically the size of the eddies across time scale, across spatial scale. And so we can get this power law structure. And when we logarithmically scale both sides, oh, I left it out of the x-axis, I'm sorry. But we get this linear form. So the logarithmic, that the horizontal axis should say log time scale, I apologize again. But once you log scale both sides of this relationship, then you end up with a linear relationship whose slope is the exponent that we saw on the left. And that slope ends up being pretty important for describing how well the fluid system is exchanging information, energy, across different scales, how well it's interacting, how well different scales of activity press on other scales of activity. So we can estimate this H by taking the linear fit, and then that slope there is a nice estimate of how flexible how responsive this system is. And so the constant slope here it has a geometrical interpretation, but basically what it means is that we have a symmetry across scales. That's not to say that all the same materials are exactly the same everywhere you look, no matter what grain you take. You might have new descriptors and new observables at different scales, but the form of the way they interact, that seems to show some symmetry, some sameness. So fluid dynamics actually has led to a lot of interesting observations that I think are going to have progressively more impact on psychological fields. So this idea that fluid systems are very textured, have a lot of internal structure that we'll see as we zoom in, but could miss it if we didn't. So this phrase, big worlds have little worlds that feed on their velocity, is a line of satirical poetry by Louis Fry Richardson, who is studying sort of how hard it can be to actually quantify flow. He would ask seemingly ponderous, silly questions like, does wind have a velocity? And so one of his jobs once upon a time was to start to sketch out a stream in a peat field to figure out where it should be carved so that people could manage flooding. So what he was interested to sort of like, how does this stuff work? How does it flow? And so we end up with a very behavioral science problem in the middle of this fluid dynamics project, interestingly. So you can ask a question about, how representative is your sample of an individual actor? For Louis Fry Richardson, it was how indicative is the average flow across a sphere of fluid indicative of particle flow. So the fluid is obviously composed of a bunch of molecules of water, and those molecules have definite trajectories that we could measure if we knew everything. The question is, can you take a bunch of those molecules together, look at sort of an average, a large sphere within that flow, and examine based on the average endpoints of all those particles? Could you determine the trajectory of a single particle? Turns out, no. So you can look over progressively finer scales, and the problem is that you can get, so you'll definitely get a dwindling of this sort of the variability there, but it doesn't dwindle fast enough. So as you look across progressively finer scales of time, you get a frustratingly persistent amount of variability in the trajectories of these water molecules. So we can think about this as psychologists, where we're thinking about the average perceptual response for a random sample of participants and ask, is that equal to the individual experience? And it probably isn't. It's and so we have folks like Fred Hasselman and Peter Molinar and Madhur Mangalam asking very important questions about ergodicity. So this doesn't actually work very often for fluid systems. It can be the rare case that the average is representative of the individual. So the issue is that within these fluid flows, there's a lot of internal structure that we don't initially see, but we hopefully will. So you see inside these samples, a lot of sort of coils and vortices and eddies swirling around, knotting up all of these molecular trajectories. And so we can sort of schematize what we had last time with this new image here, where we are understanding that each of these smaller samples is nested within the larger. And so you just keep getting persistent structure as you zoom in within nested scales. And that symmetry that we saw last time, that's sort of available in this schematic here, where we can like describe the logarithmic slope across the different scales. We can take that slope and use it as a way to estimate the flexibility. How context sensitive is this fluid flow because of all this internal nested structure? How tortuous is it? How many new structures could it form? So this stream metaphor that we've seen in psychology for a long time, and that, as we saw in the last talk, the the ideas from James are very much at the forefront of these ecological considerations. His idea of the mind as a stream, I'd say that still maintains a lot of force. I think it's time to sort of dig in with the fluid dynamics state of the art that we have now and see what we can get from these metaphors. And so I think there's a real possibility if we start looking at these symmetrical relationships, these slopes with H, these relationships could offer us some insight into how the laws of fluid dynamics could support our freedoms. The laws very often seem like sort of prohibiting, delimiting things. They might actually support real possibilities. So that's sort of a different way to think of laws, not as enforcers. They offer up the possibilities that constraints will enact. So that's a very Howard Petit idea. I think, I hope I'm not misusing his work. But so could these laws of scaling that we begin to see with turbulent fluid flow or just sort of meandering stream flow, could we get ways to explain how we perceive and act differently and even learn? The way we explore, certainly, ecological psychology wants a lot to know how we explore our surroundings, how action generates perception. How we explore, if you looked at how we reached out into the world, does look like a cascade. So it's sort of, and what that means is that it's clumpy, it's patchy. It spreads out in bunches. There's nested structure. Each step forward is nested within the previous steps forward. So let's pretend we are an exploring organism starting out from wherever we are to perceive, well, whatever's out there. So you can sort of think of us as a point mass organism about to reach out. You can also pretend you're just a physical event spreading out, generating stimuli in a social kind of sense to be perceived by some other organism. To be honest, like organisms and environments, they are streamy things, I think. I think that's an important recognition here. So they spread out and flow in sometimes chaotic ways. Perception, I think, has always been, and I think ecological psychology taps into this, has always been the question of figuring out how shapes that govern, how shapes govern the contact between organism and environment. Ecological psychology is about how organisms fit as they spread out. What pushes them back? Where do they keep moving forward? So the geometrical question is, are organisms exploring, are they flowing into their worlds evenly, homogeneously, and not hierarchically? So is there no nesting here? In which case we would get what you have with a random walk from Carl Pearson. You have this sort of progressive spreading out where you're ready to hear and see ever more in all directions in equal measure. That's one way you could be exploring. That's one way you can find flow. But the alternative is that we have uneven, clumpy ways that suggest hierarchical flow. If your extensions into the world as an organism that wishes to explore and then to perceive, if your intentions guide you in a certain direction, you're going, I think, to sort of step off and branch off from where you've been in the past. And so I think there's going to be a little bit more clumpiness. There's going to be a little bit more history where the current postures and the current configurations of our bodies and our behavior are going to be very contingent on where they were previously. So from panels 1 to 4 to 5. In a way that reflects sort of a choice. It reflects biases. It reflects how we're built, being sort of, and how we wish to learn more and explore more. We push ourselves in specific directions. We're not, as much as we'd like to be, we're not always as even-handed and evenly distributed as we'd like. We reach where we would like, and so an intention has got to be a big part of ecological psychology. This pitching forward in one direction and not another. So we look a little bit more like what's in these bottom two panels here. And that clumpiness, that tendency of things to break off in parts that existed before, rather than in one even spreading outwards, that's a glimmer of a cascade. So so that can be percolating at scales we don't even see. So fluctuations that we can't see, like in the fluid flow, in the stream example, that that can one day burble up and generate rhythmic behavior. So this is kind of like riffing on that idea from the Turing instability. We can take the Belousov-Zhabotinsky demonstration, which is it's not a living thing. This is just a petri dish full of bromine and acid mixed up together, generating just enough of a chemical instability that you can't see. And very often it won't do much. So this is a very intermittent thing. It was hard to pin down initially because it was so intermittent. Sometimes it'll just sort of sit there placidly for a long time when you might hope that your colleague could see it. And they might start to wonder, where is this? Has my colleague gone crazy? But no, so once things kick off, you can find that this bromine and acid solution will self-produce these concentric rings. And so there are other versions of this that have more global oscillatory properties. So this is just one preparation. But what you're seeing here is sort of the generation of coherent clocking periodic forms from what seems like nothing on the left, but is actually these low-level, very small, fine-grained chemical instabilities that somehow percolate upwards to the bigger scale. So what we're looking at is an interaction across timescales that's giving us these interesting periodic forms, which are actually context sensitive. If you look around the rims, these outwardly expanding ripples are bouncing off the edges of the petri dish. So you can, there's the beginnings of some context sensitivity in this physics demonstration. So what you have here is concentric periodic behavior that folks like Pythagoras or Plato or Euclid would love, based on nothing but subtle instabilities here. So this is sort of an example of that third insight from Turing that I called out before. So what if our perceptual experience is a fluid harmony self-organizing from fluctuations nested in context? Okay, so the idea is that maybe the harmony, the Pythagorean balance and all that stuff isn't there at the start, but we get to it. So small scale instabilities nested within this seemingly homogeneous thing can billow up outwards into bigger scales to give us interesting coordinated forms. So what if this were a perceiving organism here and not just a chemical solution? Crucially here, there's no logic, symbolic, or representational codes and control. So there's nothing planning this. This is pretty messy, context sensitive, could happen in a lot of different ways. It's actually really flexible. As we see, it sort of bunches up against the rims. You could stir this up and sort of spark new concentric ripples by like stirring it up with a swizzle stick. So this is ready to move and shift according to context, but it still has this interesting coordinated form. So we see this sort of mix, this tension between what look like rules and what doesn't look like rules at all. So what if this is a fluid cascade of interactions across multiple scales? So we can take our fluid layer example. We can sort of note that we have these energy distributions entailed by context. So turning on the damn flame, that presses into and against the internal distributions entailed by molecular patterns. And so you get sort of this knitting together of context with internal structure. And that's sort of embodied by the Rayleigh number, as we saw. And that relates back to how well the system can deal with the contextual energy distribution. So the fluid is dealing with the temperature gradient that you imposed based on how it reshapes itself. And that has a consequence for how steep the temperature gradient is. And so in the meantime, you get, as a consequence, incidentally, often, new structures. So the convection cells, and then the turbulent eddies within eddies. And then those can, in turn, sort of mediate how the structure is reshaping the contextual pressures, how it's changing the temperature gradient. I'd like to sort of put a more biological garb on this and say that this is very much what we're doing when we, as organisms, are stomping around in ambient energy distribution. So if we think of energy as sort of as a big patterned mess before us, we're stepping into it and changing it and reshaping it at many different scales. And it's actually also changing us at many different scales. But so we can think of the organism as a hierarchy of multi-scaled responses to ambient energy. So there's the big contextual stuff, there's intention, there's task, and then there's the small receptors also participating, and they all, they have to be working together in some sense. So what if they're all working together through this cascade framework in which we sort of have a geometry for looking at how different events at different scales interact with each other. So cascades offer a geometry. So it's a way to look at measured behavior and to actually sort of take stock of its shape and to sort of look at how clumpy it is, how even it is, and to sort of use that as a way to say something important to theory about the interactions across scale. Very often this geometry will not sort of follow what we learned in grade school. So the dimensions, unlike in Euclidean geometry, may be fractional. So that's not a comfortable concept for a lot of us. But dimension isn't just sort of how many axes you need to describe your object. It is secretly, or less obviously, it's about how systems spread out, how many different directions they spread out. And sometimes the spreading out requires that new axis, so a first, a second, or a third dimension. But sometimes it's just sort of straining between two full-on independent axes. So fractional dimensions are actually easier to find than you might think, as odd as they sound, when you're looking at fluid dynamics. So we saw some of our first when Edward Lorenz was looking at convection flow through three different equations. So he built a model of convection. So he was approximating the Navier-Stokes equations with three ordinary differential equations. So there was nothing controversial in any of those. They had, each of them were sort of tied into each other, which was sort of a normal way for physics to proceed. Variables push on each other. But then he noticed that basically when he did this, this reduced model for the Navier-Stokes portrayal of convection, he noticed that he got something he wasn't expecting. He got a deterministic system because there are very few differential equations that governed exactly what happened, but it never repeated itself. It gave him these very strange trajectories. It looks like a butterfly, so sometimes we will shorthandedly call it the butterfly attractor. It can actually this system of equations can actually take on a few different forms, but the butterfly is the best known. Each of these equations are modeling very concrete physical properties of sort of how convection happens. So what's interesting about this system is that it does not fill the three dimensions. So not only does it not repeat, it's not using most of the three-dimensional space that we would give it. So having three differential equations should give us adequate, sort of give the system free rein to move across all three different dimensions that we're seeing plotted here. So the plot on the left has an X, a Y, and a Z. The X is horizontal. The Y is sort of is slanted away from the horizontal, going from 50 to -50 on the left, as you can see. And then the Z is the vertical. So what we're doing, this image, the blue dots are a bunch of points that are the output of the three equations on the right. So the dx over dt gives us the horizontal coordinates, the dy over dt specifies the position on the receding axis from 50 to -50, and the z, the vertical axis, is defined by the dz dt equation on the right. So what's interesting about this system that's not actually filling three dimensions, it has a fractional dimension. It's 2.063. And that's to reflect that it's basically a flat surface sort of bent a little bit. And so in the midst of that bent surface, you get an attraction of the points towards that sort of small region. And then you also get within that region self-avoidance. So this is a really strange kind of behavior, and this is called a strange attractor. It's strange because it doesn't have a Euclidean dimension. So its dimension is a fraction. And so this fell naturally out of a model of fluid dynamics, which is sort of weird and surprising. But we can find this in human behavior and perceptual response all over the place. So we can find that a lot of behaviors, cognitive, perceptual response behaviors, come in clumps and spurts. So they suggest a fractal system with a fractional dimension. And we can look at the work of Art Bills, who I didn't know about Art Bills until Guy Van Orden brought him up. But he did a lot of work with speeded perceptual tasks. So he'd ask people to respond to a prompt repeatedly, and they'd have to sort of give their answer as fast as they could. And he would look at the responses, these vertical hatch marks, across time, which you see on the horizontal from 0 to 40 seconds. And Bills was really concerned with these blocks. Like, these were times when the person wasn't doing anything. You know, they could clearly think they were perfectly fine, but they just sort of seemed to have some fatigue. He was really puzzled about what this was. Why couldn't you get an even response? So sort of think back to that comparison of the even expansion and the clumpy expansion. This looks more like the clumpy expansion. Bills was really struggling. He tried to sort of understand the geometry of these blocks. He would plot the length of the response intervals across the number of responses, for instance, and try to figure out like what's the proper way to measure these and quantify these. So how do I get these peaks, basically, these excesses of latency that seem to, he didn't know he didn't think that the mind wasn't working. He just sort of was starting to get this feeling that maybe the mind had something to do with bodily effort. And that at some point we had just sort of fatigued the chain of events. He was trying to understand these peaks as waves. He was trying to think of them as periodic. He was trying to think of them as scallops. He started to sort of come up with these sort of speculative theories about what if there are different separate periodic processes, different scales of activity, different scales of oscillation. And he sort of thought that they interacted, definitely, because they definitely piled up on each other. And it seemed that low-level events, like in motor activity, could be sort of piling up on our ability to process. So he's actually suggested, I don't know that he did it, but he suggested a Fourier decomposition, which is very, very thoughtful, and he sort of presaged a lot of what Guy Van Orden and David Gilden did, and then that I've done as a consequence. But what he's doing is that he's sort of showing that the system is not growing or spreading evenly in all directions. And so we would expect a fractional dimension here in these response behaviors. And sure enough, we do get them. And we've learned that the fractional dimensions are actually a consequence of interacting timescales, nesting an individual response behavior into the bigger context of all the responses and all the task parameters, or many of them. So Fourier's model, if Bills had tried it, it would have been a good first step. But Fourier's model only recognizes timescales separately and never in terms of their hierarchical nested interaction. So Fourier's problem was not perception. He was interested in heat flow, and he was looking at how you could explain a temperature difference across positions on a circular solid. And so the details aren't important, but his solution was that you could describe temperature gradients, or anything, as it turned out. That's not entirely true, but we can talk later if you're interested. But he envisioned that, like, basically anything could be described as a sum of many separate waves. And so it's not just any waves, though. He's actually thinking about harmonic waves. So he's sort of riffing on Pythagoras' idea of having a fundamental frequency and then whole number multiples, because that would sort of suggest a harmony in nature. And so you could basically take this geometry where you have the size of different waves of different length. Now, independent timescales are great, and the Fourier decomposition is a wonderful tool. Independent timescales are really good, particularly because they can sort of give us a modeling space in which we can situate specific independent causal constituents. So you have specific factors that vibrate at specific frequencies and that contribute to the overarching process at a specific frequency. This doesn't necessarily entail any irrational fractions, and it definitely doesn't describe any interactions. So this is sort of this is still a very Euclidean Pythagorean idea. And I don't mean to sort of kick that aside. The Fourier model has been very effective, especially when there are really independent constituent factors to identify. One of the examples, just as an aside, is the solar spectrum. And this is commemorated on a postage stamp. I love it. So basically what they depicted here was that when you took the light from the sun and submitted it to a Fourier decomposition, you could get this wonderful spectrum of colored light that would pop out of the prism. And they actually used this, and in particular the gaps in it, to infer the chemical composition of the sun. So they were able to pick out that dark vertical line under the D, and they were able to infer from the visible light spectrum that there's a new kind of molecule, and they called it helium after the name for the Greek god for the sun. So Fourier decomposition is like a wonderful way to probe energy absorption through our own perceptual system. It's very good for picking out independent constituents, but maybe it also has potential and can sort of give us a lens into interacting timescales. So the timescales begin to interact, for instance, when you're sort of, well, anything, but let's just think about perceiving your way to a train. So you're running through a place that probably has a lot of places to eat, a lot of distractions, you're looking around, you're sniffing, you're having lots of physiological processes that are unfolding on the fly, and then you're sort of having this ongoing check-in with yourself as to how fast you should be running, should you slow down, and you're engaging progressively more levels of your activity. So, and as you look deeper into this physiology, as you're running to the train, you can find more and more structure. So as you're doing what feels like simple thing of just trying to get someplace on time, you're engaging lots of different physical systems within yourself and connected to the context. And all of these things interact. And that's sort of the tricky part. That's what's not necessarily immediately in the Fourier model. So the question is how to express all these complex interactions across timescales. So cascades are a way to start talking about that. And cascades are a way to think, they're inspired by the natural phenomenon of waterfalls. And they refer to how to generate a measured series through through a progression of interacting timescales. So we could sort of schematize it a little bit like this and show that the river flow at the top of a rock face is sort of all homogeneous and going in one direction. As you get further down the rock face, the flow splits and splits and splits and splits. And there's always splitting based on what was split before. So the question is, how are proportions of the stuff, the water or whatever you have, how are they distributed across time and space? You begin with your aggregate sample containing 100% of the observable, all the water in the river at the top of the rock face. And then you repeatedly split that again and again and again and again. And so this is you can sort of make numbers to do this by sort of repeatedly multiplying random numbers. And you can get at sort of a portrayal of how deep the cascade is at specific depths along the rock face. So this cross section here shows us a series of proportion, how much water there is in each sample as you go from left to right on this cascade. So you can ask, how well are these proportions knit together? How well do they align across space? So these clumpy linkages of proportions across time, the fact that water bunches together and splits apart based on where it had been before, that's going to give us a view. So our bodies and our exploratory behaviors are going to look like this. And the clumpiness, if we estimate it with fractional dimensions, might reveal something about the evolution of perception action cycles. So does human action actually look like this? Yes, so many of the time. So some examples, I'll just click through. You can look at Zipf's law. As you look at the frequency of words in our language, and then you compare them to the frequency of more frequent words, so that's their rank, you can find an inverse power law, which has the same geometrical form as we saw before turbulence. And many languages actually show this, and we don't entirely understand why, but this was one of our sort of early glimpses of human behavior, even cognitive behavior, showing this interesting cascade-like structure. Bill's and his blocks were a sign of mental fatigue, but it turns out that a lot of these response behaviors where we find these things, that they actually show a power law Fourier transform. So the oscillatory power will actually decay as you get to higher and higher frequencies. So the size of the waves will actually decrease as you get to progressively higher frequency waves. So if you logarithmically scale it, you get that straight line again. Power laws appear lots of other places. I won't read the list for you, but it's sort of the list goes on. And so it's an exciting question whether or not you can look behind these power laws and find evidence of cascade dynamics. Most of the flexibility in psychological functions we need for perception look an awful lot like riverish cascades, where you have that nested structure where the texture contains texture contains texture. Internal models of the world, that's where cognitive science has been with those first two insights from Turing that I noted. And they lean on this idea that you're going to take cues into your internal models and you're going to use them to infer where you need to go. So if you want to traverse space to get to that next tree, then you have to have a model of the world. And you're using computational thought that lets us reason our way to true spatial arrangement. That's sort of where we are. We are in non-ecological psychology. So we're reasoning our way through inference to a metric of absolute space. And so that's sort of how cognitive science has tried to situate action in our context. The problem is we haven't yet found a simple definition of stimulus, and Gibson pointed this out in 1960, and I don't think we have a clear definition now. That's a wider and wider set. We're finding more opportunities and more interesting diversity of experience in that regard. So the context as a whole matters. And so very often the cognitive science explanation relies on this idea that the machinery must encode everything and let the model run faster than time to search all possible options. So this is our non-cascade solution. We basically have Isaac Newton in our head, and that helps us predict forward in time to figure out when the sort of particle that is us is going to reach that next tree in view. Computer minds are awesome. We have built them to model the world faster than time in GPS satellites. So GPS satellites do exactly this. They model the whole world and they project into the future. But the problem is that they're too committed to prediction and they do poorly under uncertainty. If the premises for those predictions falter, then we're in trouble. So GPS models in particular are good for 4 hours, but they actually need to be corrected in half that time. The reason why is that we have things like solar radiative pressure. And so we have sort of background forces that are bobbling the satellite off course. So prediction from models is vulnerable to unpredicted perturbations from context. And the burden of keeping these models falls on intelligent agents like the engineers on Earth who can sort of correct the model of the world and send it up to the satellite and keep things rolling. So if the mind is always and entirely a computer, we're actually in trouble. And so if it's not only a computer, what else do we have? So here we are feeling Luke Skywalker's problem. If you don't use the computer, what else do you have? My answer, my thought, is that perhaps we have a cascade at our disposal. You can look at how human perception action do under unpredictable conditions, and they don't do as bad as model-based prediction would suggest, actually. So you have examples here. Speech articulators can compensate really fast. So this is the work of Tuller and Kelso and Fowler. Human participants can, with practice, improve their ability to predict mathematically unpredictable sequences. So even if we are forcing the unpredictability and we can program it even, participants are pretty good to sort of make do somehow. So they clearly have the goods on mathematical structures, even when they are duty bound to be unpredictable and random. In particular, I'm referring to the logistic map here. So, so this model can be set to a chaotic phase, and then people can forecast where on the screen the next position in the chaotic logistic map the next dot will appear. Motor systems all over the place. There's so much research on this, it's amazing. Motor systems are able to coordinate with unpredictable stimuli. So what we call prediction is not very frequent or necessarily adaptive. And I think it's actually instructive to see how people are actually talking about this. So these are quotations. When you ask the body to do prediction, sensory feedback becomes critical when predictions are erroneous or unavailable. And it turns out we have noisy nervous systems. So using sensory information can lead to large errors. So we're in a tight place. And it's hard to know how prediction is going to work when we have noisy nervous systems, and then our predictions are high stakes things that maybe don't have anything predictable out there to sort of be founded on. So how could an organism ever manage to coordinate with events? So where prediction fails, I would say Cascade Dynamics, so that multi-scaled organization may support us. And so we have this sense in which organisms might be themselves large multi-scaled organizations, where you have large events setting off a chain of progressively smaller events. So from neural impulse from the brain, if you like, down the spine to all these different parts on the periphery. There's no necessarily principled center, because these fluctuations can start anywhere you please, anywhere there's important contact with constraints. And there's this intricate spreading of fluctuations coursing and splitting across the body. So what if the role of experience in a perception relies on this bodily hierarchy? What if we're always talking to this? What if it's not in our neurons or our genes, or some of it is, but it's also in all these other parts too? So brainless and neuronless perception isn't even magic nonsense. So it sounds strange to even sort of ask about non-neuronal stuff, but I like to bring up the example of slime mold, where the hierarchy here blurs the distinction between single organism and groups of organisms. So we have Dictyostelium discoideum, and it is an amoeba that becomes a nada amoeba. So it can start its life cycle by itself, eating, and it's really tiny all by itself. Once the food runs out, it sort of clumps together, and it can take multiple shapes. It can be, and so its job is to basically get the folks together to find a place to put down roots for the next generation. And so it will sort of group together with other former amoebas, and it will form these slugs to navigate to a good place with more food, or it can set up a fruiting body, and then it can basically project spores, which are going to support the next generation. And it can do this without, there's no nervous system. There is, in most cases, only one cell at a time. And then you get these cells pressing together and coordinating and differentiating their abilities. Actually, once they're in this larger form, they can generate new kinds of behaviors to support the future opportunities of their offspring. So, so the next generation begins again with plentiful food, and so there's a lot of future tending behavior here with no nervous system, and there is this multi-scale coordination where the single organism never quite goes away, but it sort of fades into this larger multicellular organization. So. Is it one organism? Is it many? It's not clear, and people puzzle over this, but the blurriness is key for adaptive response. So the fact that we can't say which is the organism and which is the group of the organism and make it clear once and for all, that blurriness is sort of crucial to the survival and the sort of prospective behavior of this species. So this aggregation is pretty fascinating. So I have some videos just to show you how it looks. These are these tiny little guys who are glomming together, gradually sort of losing their individual identity and sort of ceding control to the larger structure. And this is what they look like when they're sending their spores out. There we go. And this is a wonderful example of motor coordination here with a slug. That you can see this helical motion of the individual cells. I love this stuff. So organisms are breaking these boundaries all the time and shuffling up and down these biological hierarchies. So the functional wholes are never just the sort of ingredient list. It's always these relationships across scale. So they appear, they disappear, they aggregate and break down all the time. So I think we do this too in a different way. So we do this without sort of breaking down our cells every 5 minutes, but so our ability to perceive and our ability to explore to perceive reflects and exemplifies this capacity to zoom in and zoom out. So zooming in would be operating at molecular scale in response to these tiny stimuli, and then zooming out would be like sort of taking in the big picture and responding to task and intention, large scale context. So all of these interactions across time, they give us a way to tap. So we can measure all of those, take their standard deviation, look at that relationship with scale, just like we saw with the responsivity of turbulence. Now we can actually measure this in human behavior with a standard deviation, and we can estimate this fractal exponent h. And we can sort of use the same logarithmic scales to estimate the slope of that relationship as a line. And that h, which we've seen before, now we can sort of apply that to measured behavior, and it can answer the question for us: how strong are relationships across measured timescales of behavior, of our behavior? We can test this idea. We can sort of give this cascade organization empirical rigor. So we did a study a while ago looking at a metronome, and we understood that lots of metronomes were periodic and would give regular beats. We wanted to break this and to give people an unpredictable signal. So it didn't actually look like this. This is just a cartoon to indicate that we gave people a metronomic signal whose onsets were spaced with so something like Bill's blocks. They were defined by a chaotic map, so kind of like the logistic map. This is what it looked like. So the inter-onset intervals were sort of hovering between 1 second and 1.5 seconds. And we wanted to know, what would people do with this completely unpredictable signal? How could they respond to it? And they seem, when you look at the long time series, they look like they're in the ballpark. It's really hard to sort of compare individual beats with taps though, because people would feel like they forgot, and then they double tap or they triple tap or they miss one, but they seem to somehow tap into some of this temporal structure. And so what we found is that actually under this uncertainty, when there's no computational prediction to be had, the fractal scaling matches. So the fractal scaling of the metronome predicted what the fractal scaling of the human participant data would be. That was a pretty strong correlation. But more than that, it's not just sort of like there's this average measure where they sort of pick up on just how it is in general. There's this finer grained control. And this is where multifractality gets into the picture, where you can look at multiple fractional exponents within the same time series. So there's this diversity of fractal scaling, even within the simple single trial of 1,000 onsets here. So the rises and falls in fractal dimension in the sequence of behaviors is specific to the rises and falls in fractal dimension in the sequence of onsets. So that where there's uncertainty and unpredictability in our context, there is sort of a cascade structure. So the randomness that we sort of see out in the world has cascade structure to it. And we seem to be able to lean into that and tune into it. And actually, we're able to let our bodies coordinate, even when there's no sort of explicit foothold for us to infer what to do next. So Could cascades save us from needing to know everything before we can perceive it? That would be the hope. So the problem with Helmholtz and the problem with the first two Turing insights alone is that you really need to know a lot before you can perceive. Prediction definitely happens, and I sort of want to talk about that, whether or not I'm an ecological psychologist. And so we can use computers and we can sort of make those models. We do it a lot. But the important question is whether prediction is always the basic foundation or inference. And I don't think it is. If it's always prediction, if it's always inference, then perception is difficult to explain when events are unpredictable, when you might slip. So we have this problem of not knowing everything that we'll need to know. Cascades might not care. They might give us something to lean back on, to sort of coast along with, even when we don't know what matters. So we can, in fact, turn the targeting computer off, and we have these larger structures wrapped around us in the context and also flowing through us in our bodies, across our behaviors. So could cascades even be the foundation for supporting this faculty of prediction? So the evidence that I shared just in the previous slide, that's sort of, it seems to suggest that this isn't entirely crazy. It's worth pursuing. And this fractality and its variation in multifractality might be an important concept for exploring these possibilities. I have a lot of people to thank here, so I hope I didn't miss anyone. I really appreciate being invited to talk, and I look forward to any questions. Thank you for sticking with this talk. This is weird stuff, I know. Thank you to my family who has been through me through a very tough transition to a new place where I'm very happy to be, but thanks, thank you.
Okay, Damian, thank you for that talk. That was absolutely brilliant and very captivating. So, wow. Let me steal the first question, if I may. And this is something that was just coming to me as you're, going through all these different scales at which we run into these cascade dynamics, the fluid dynamics, and all of these multi-scale interactions that are, they're not the neat, clean, Euclidean, Newtonian type of stuff. How do we live in a universe like that and get to a point where it appears to us, or in sort of popular discourse, that the neat, clean Euclidean stuff is like primary? How does that happen, that we don't perceive all the fluid stuff as being like ubiquitous as it is, and somehow we have this perception of like things being kind of like the neat geometrical things that we see?
I feel like that's a question you've asked me before, and I feel like it definitely warrants figuring. I don't know entirely how that works, but it is. I think it's, so a few things. I think it's interesting. There's a lot of information sharing on a lot of scientific discourse that I feel like we absorb through our culture in ways we don't even know is culture, and that we're getting it from somewhere. I have really fascinating discussions with people, especially in the classroom, where we talk about the sense of three-dimensional space, and we take it so for granted. We take it like that it must be so that we think of space as homogeneous and empty. And it's always interesting to think back to that time. And I can't imagine what it must have been like when Isaac Newton himself had to sort of argue for the idea of empty space that was homogeneous and that wouldn't change how things, fit. So I think it's hard. I think definitely scaled things and Euclidean shapes are, that they're an easy place for us to consolidate and collapse our degrees of freedom, for sure. But I don't know. They might be some sort of. They might be that might be one way to think about them. They're a way to collapse a lot of complexity, and we fall into these patterns, sort of like Jungian archetypes. I think that the fact that we're compelled by those patterns, they're there. I don't want to disavow them. I just think that we're very good at manipulating those in a way that might not seem so Euclidean either, though. So when people were starting to do statistical physics, they started to treat vortices and eddies as if they were like their own molecules. And so we had the idea of sort of like the tiny little particle, but then we're ready to think about a larger particle. And so like, we're definitely like taking a spheroid and like projecting it into a bigger spheroid. But even just that ability to sort of like scale up, I feel like those are sort of like fissures in the Euclidean, the seeming Euclidean fantasy. So like, as we've manipulated these things, I think we show how they've never been exactly what we said, like a point being sort of without length or width, like that's fine. But then we sort of project them into a line with finite distance, and then it's always mystified me how we got comfortable suddenly with that having a finite definable length after the point's not. So like, so we definitely have these patterns we fall into, but we played fast and loose with them, like as long as we've had them too. So it's sort of, I think it would be wonderful to run studies on sort of understanding how kids, which I'm seeing at home, sort of fall into these patterns and use like triangles and circles to like represent like craggy things. So I don't know. I wish I knew more, but it's a fascinating question.
That sounds actually like a fascinating research question right there. So.
My daughter was recently asking me why, when she draws people, she needs to make lines, but when she looks at people, she doesn't see lines. So it's sort of an interesting, just the issue of a contour is really tricky.
That's a good question. Okay. We have a question from Alan, and it says, in your view, what is the relationship between Cascade Dynamics methods of prediction and machine learning / AI?
I think machine learning and AI are very good correlation hunters. So you could probably ask AI to run a lot of fractal analyses in a lot of different places. So I don't necessarily think that one is going to give you the other. So you can do things like that are sort of hierarchical cluster analysis of your AI generated or AI collected analyzed data. But I think that but AI is more so about correlating a lot of measurements at similar scales. And so you end up with pairwise correlations, very large pairwise correlation matrices, and you don't get to see as often the relationships across scale. And then in order to sort of tap into Cascade Dynamics, to make that case that this is actually a nonlinear process that's progressing across different scales, very much of the work involves testing against linear surrogate time series, so making up synthetic data that will actually mimic the cross-scale relationships I'm seeing, but for strictly linear reasons. And so AI there's no principal reason why AI could not incorporate synthetic data, and I don't know enough about it to say that it doesn't. But I feel like it's not. So what we're doing, the nonlinearity that we use in our bodies as we project our cascades forward, is not just the sort of large scale correlation hunting that a lot of AI does.
Excellent. And I'm going to just kind of build on that and ask, is that something to do with the time scale of evolution, do you think, or is it like an innately biological thing, or is this something that potentially can be overcome?
Which you want to
sort of like the differentiation that you make between correlation hunting and the sort of cascades.
Oh, well, I think you could, so with AI, you end up, there's no, I'm using computers to do my fractal analysis. So like in principle, there's no reason you couldn't do it. It's sort of like, I think one of the reasons it doesn't come naturally is that the computers are churning. When you try to automate the correlation sensing in that sense, what you're doing is you're automating logical processes running at specific scales to do their job. And so you end up investing in very specific scales and so a computer is by definition going to always be a scale dependent machine, which I'm borrowing that language from Howard Petit as well. Sort of like you have your scale dependent symbolic processes, which are running the AI. And what we're seeing with flows and cascades is rate dependent. And so you're sort of, so I don't know if there's overcoming it. I mean, I think what Petit says is that the two are complementary and one should live with the other. So like, as we build AI like capacities, whether through computers or through any sort of logics that we use behaviorally, the way we orient them and tilt them and tune them into this or that, that's still got to be cascadey in a way that is not, that you can't fully decompose the cascade into a lot of scale dependent processes. Like you can't sort of like pixelate one, coarse grain it into the other. And in fact, I don't think you want, so in terms of, I mean, and Petit would actually say that all of evolution is actually about the coordination between the two. So in that sense, I don't think one is necessarily there to overcome the other. I think an interesting question is how they coexist and mutually support the other. I think one of the reasons we're able to make good AI is that we have a cascade process that lets us be a good computer programmer and hardware engineer and stuff like that, and figure out a research question. Like, so I love what AI is able to do. I don't think that it should be broken, or that the cascade needs to be broken down into an AI process either. Like, I think I'd like to see them live together.
Excellent. All right, we got a bunch of questions coming in. So let's go with Adrian. And Adrian says, I'm curious about that last bit with the chaotic metronome. It wasn't entirely unpredictable since there's autocorrelation. What sorts of differences were there? Age, area magnitudes, etc., with brown and white metronomes.
So this was not a brown. So I wasn't using brown or white noise. That would be very fascinating. I know people have done that. There were the chaotic regime of the Ikeda map was based on lags, and I manipulated to have multiple different lags back. So the current values were dependent on a previous value deep in the history, and that led to changes in the H value for sure. So the reason that I'm pretty, you can look at things like linear redundancy too, to talk about the sequential dependence autocorrelation for sure. So the reason I'm pretty sure, and I didn't sort of I didn't belabor the slide, but I'm happy to talk and point out more detail, and which I have in papers out there. But what I was doing was I was comparing the linear structure of the metronome and the linear structure of the response behavior to their actual measured response behavior and the actual produced onset time series. And so I actually had sort of like a horse race between the surrogate data for the metronome, the surrogate data for the participant, and the original metronome sequence and the original response behavior. And so I was looking for like which explained the response behavior best. And so it was the original rather than the surrogate set of the metronomes that predicted the original response behavior. So surrogate testing allowed me to pin down the fact that it was more so the nonlinear aspects of the multifractality in the metronome that predicted the nonlinear properties of the response behavior. So I was definitely being shorthanded and in schematic in that slide, but there are sort of more stringent tests of the actually nonlinear aspect of this relationship. So the surrogates, I should note, have all the same linear autocorrelations. And so they already build in that structure. That helps.
Okay, excellent. All right, we have Travis. He says, enjoyed the talk, Damian. Have you ever explored differences in fractal scaling at different scales of analysis, e.g. neuro versus behavioral, as opposed to multifractal analysis applied to one composite or higher order signal suggesting interactions across scales?
Yeah, so I think I think that's a very interesting question. And this is sort of like multifractal is actually a very large term and concept. It's sort of been the umbrella for a lot of different traditions. And there is within it this sort of interest in the different kinds of scaling across different parallel scaling across different scales. So that's an important question. My own research hasn't gotten into it too much. What I have done though, I mean, what I've started to get into is looking at scaling behavior of different behaviors with different, well, I guess it is this issue. I just hadn't thought about it in these terms. But so some more recent research I've done has looked into the speech signal and looking at the multifractality of the speech signal as recorded at 44.1 kilohertz. So that's a very fine grain. And I've been looking at how that multifractality there supports language perception of the speech. So, and it does have some significant contribution there. So the multifractal nonlinearity of speech filters into our impressions of what the intended meaning was of that spoken burst. And then at a coarser grain, I've had people. So I've built that comparison into a task where people had to self-pace what they listened to. So they had to press a button for the next speech blast, speech sound. And so I've looked at the multifractal scaling of the button presses, which are at a much coarser grain. There are much fewer of those than there are measured pressures in a single spoken sound. And so, I've looked at how the multifractal scaling of that button press at the coarser grain supports memory for the speech. So I guess I'm sort of backing into exactly that issue where I'm looking at the multifractal structure or fractal structure at different scaled behaviors and seeing how they contribute to a task. I haven't done sort of what might be the more rigorous issue of looking at the network relationship of those fractal parameters at the different scales. So it would be cool to see whether there's statistical relationships between the sort of fine scale speech process and the coarser scale button press. I think that takes a lot of data and a lot of planning that I haven't gotten to yet, but I think it would be really worthwhile to sort of figure out what, to the degree that we definitely have these different measurement scales. You can probably find these sort of relationships of, say, EEG data and speech data and button press data, each unfold at different timescales themselves. So you could probably find, and it would be really interesting. So if Travis ever pursues it, I'd be really interested to hear more about it. But I think there would necessarily be statistical relationships that, and I don't think you would get sort of a monolith of just sort of one fractality for all the different kinds of measurements at all the scales. I think you are going to get this interesting texture. So I've sort of been creeping up on it, I guess, through speech perception and memory for speech, but don't have sort of all the network modeling that question would deserve.
Excellent. All right. Next up, we have Raul says, thanks for the talk, Damian. A question: we can determine the H scalar. We can show these cascades, but how do we then explain anticipatory behavior and predict whether in some situations behavior is actually anticipating a future situation using this approach? So I think, to summarize that, is that a question I think about, is there a mixture of maybe weak and strong anticipation?
Sure. I think so. Yeah. And that's a very interesting question, because it does get to this. I am comfortable with the idea that we do predict, we do use symbols to relate to our future. And so I would be curious where the model is and what we're using to stand in for the symbols. I don't think they're going to be in the head. I think they're going to be somewhere bleeding across from head to body to context. But when we're using those structures, I think they can definitely help in the way that constraints would always sort of shape flows. how it how it happens, I think, in terms of explaining anticipations, I think one way to think about multifractal scaling or fractal scaling or cascades, if we want to keep it in those terms, is that you have a single moment is never it's never like removed from the rest of the time. Just like a single position is not, or a single body posture is not isolated from the surrounding spatial layout. I think every moment you're in is not some sort of like pin's head that you can sort of balance on, and then you tip over and fall off into something else. What I think what it means that we have cascade structure in just sort of our standing still, waiting for something to happen. The fact that our bodies show these cascades show that they're tied into events happening at many different scales. And so one way to think about anticipation is that we are invested in very quick, brief events, second to second things, but also we are every time we look ahead 5 minutes, whatever looking ahead entails, we are also in that moment that we're not quite in the next 5 minutes for. In that moment, we're coasting on the past 5 minutes as well. So it's not, so we're sort of, there are multiple timescales of events unfolding all at the same time. So I think it's not that we are in a current moment divorced from the future moment, and we have at some point to definitely use the other tools to reach out and get something we don't have access to. Right now, we're living in sort of an extended moment that sort of is that has some, it's headed somewhere already. You're not going to find someone sort of like up in the air and not heading somewhere, even if you seem like you're standing still. So I think I'd be happy for, I am happy for people to use models. I've published a bunch of models myself, so I have to be committed to this idea, and I want ecological psychology to learn to talk about models. But I don't think that that's going to involve sort of the usual cognitive science suspects of Bayesian inference in hierarchies of the neurons in the brain as sort of like where that ends up happening. Does that answer the question?
Excellent. Okay, let's go. This is an interesting one from Charlie. And Charlie says, cascades flip causality around where stimulus becomes a universal and constant perception action cycle. So what happens to the distinction between correlation and causation at the level of perceiver? How could an organism be sensitive to not just what is perceived, but also what is veridically perceived? Would you say continuously corrected correlation implies causation? At what level can that inferential leap be made?
So I think, okay, so a few things. One, I'd like to make a shout out to John Dewey, who I think wrote the prologue to Gibson's 1960 article about what is a stimulus. I think we've been sort of trying to wrestle with the co-implication and co-entailing of all these things for a long time. And John Dewey wrote this wonderful article saying in 1896, we have too much data, we have to tie it all together and understand it. And that was back then. So how would he feel now? I don't know. But so he basically was saying the reflex arc was a diminished expression of what was actually going on. He wanted to talk about this cyclicity where you only saw the stimulus based on where you were, how you had been reaching out into the world. And so really, there wasn't so much a reflex arc as this sort of perception action, sensory motor chain, but it wasn't a chain because it was sort of spiraling, and it was spiraling at branching and all these multiple different scales. So I really feel like he sort of was laying down some key foundation for ever thinking about fractal processing in perception and action. Whether or not it flips causality because we're talking about correlation. So again, correlation, I think, in the statistical sense is just, it's a pairwise relationship of measurements taken at similar scale and hopefully concurrently. So I don't know if this is all correlation. So there are relationships across scales, and you can have bidirectional relationships, but I don't think that it necessarily is always the same bidirectionalities. I feel like I first heard it from Tony Chamorro once, that like you don't have to, so that cognition and mind and all these relationships don't, sometimes they move and they act at different levels of the system. You don't have to have everything working in lockstep where you have all the same interactions, all the same places at all the same times. You're going to have asymmetries, and sort of things can percolate up and percolate down. And I think it is an interesting challenge how to start modeling that, because we need to have a way to start talking about unique effects. And so it's so this is part of why I've gotten into concerns about ergodicity in causal modeling with Madhur Mangalam. And so I think that there's some real challenges here, but I think I feel like we don't have to flip over too much of what's understood about causation. In terms of causation and correlation, I feel like I think there's the meme out there that correlation is not causation, and that's totally true. But even as someone who teaches research methods, I realize I have to like pull back and say, yeah, but you need correlation in order to show causation. So the issue is the correlation never quite goes away. You just need to have it's not simply correlation. You need things like precedence. You need and sort of co-varying out competing other factors. So I think the issue of correlation and causation is fascinating. I think the Cascades definitely press us to come up with more elaborate senses of what cause means, especially as we do what Travis was suggesting, is sort of like going from one measurement scale to another. I think that's really going to force us to think really imaginatively about how that should be modeled. But I don't think I don't think it upsets too much. I think Cascades actually live pretty comfortably in a lot of relatively pedestrian physical processes that have already been, not fully understood, but investigated pretty well. So I'm not too worried about having to reinvent causality.
Excellent. All right. That has been, I think, a good, very engaging Q&A session. And we want to thank
I appreciate
Damian.
All those questions.
Yeah, some really good questions in there. See some discussion going on in the chat as well. But yeah, we want to thank Damian, I'm sure on behalf of everyone, for just a brilliant talk that I'm sure I'm going to listen to a number of times again.
Thank you.
So thank you for that, and for putting that resource out there for people, and for all of the work that you do, sharing these resources with people.
Cool, thanks. Great, well, thank you for the opportunity. It's been I've appreciated the input, and if anyone wants to follow up on the questions, I would love to hear from anyone, because I'm sure I didn't have enough time to adequately
awesome.
cover. So yeah.
Should people look for Twitter, or do you want
Twitter be great, other Fuvian.
Okay.
Or if they prefer email, I'm at fuvian@gmail.com. So
okay,
that'll work.
Excellent.
Great.
All right.
Well, thank you, David, for organizing. This is a great service.
Okay. Thank you again, Damian. All right. And we will see everyone next time.
Bye-bye.